Hello, Earth Science students. This is Dr. Hurt. Welcome to your 23rd lecture on weather. So we're going to be rounding out and finishing our whole weather atmosphere segment of the class. And after this, all we got is 1 week of astronomy, and then we're all done. So we're getting near the end here. I hope that you are already starting to review and get ready for your final exam, because it is coming. And it's not an easy exam. Well, you've been through this already before, so you know, but it's not an easy test, so you're going to need to buckle down and study and prepare for it, and it needs to start happening now. So just yet again another warning for you about that, and start studying now. And my very earnest recommendation for you is to make flashcards. I think that really helps. Start going through the lecture assignments, turn the questions into flashcards, and proceed that way. Remember, it is a cumulative exam, so everything from day one is going to be on there. Okay, you're going to have a little flavor, little taste from every single lecture, and also possibly things from your book as well. So I know I don't talk too much about your assigned reading. Maybe I should talk about it more, but you do have assigned reading, and there can be stuff showing up on the exam from that. So anyway, without further ado, though, let me get started on today's topic, which is weather patterns. So we're going to be talking about some of the big weather phenomenon that we have here. Especially, you're probably interested to know about hurricanes, and we are going to talk about hurricanes today. So just a little bit of review. How do clouds form? Okay, this is an important topic for today because a lot of our quote-unquote weather has to do with rain, precipitation of various kinds, and all that precipitation starts off as clouds. So how do clouds form? Well, remember that clouds form when a parcel of air reaches its dew point. Okay, so there's humidity in the air, there's water vapor in the air, it's invisible, you can't see it. But when you hit the dew point, that's going to cause that stuff to start precipitating out. If the dew point is very low, like let's say 10 degrees Fahrenheit, that means that the humidity is very low. If the dew point is very high, like 72 degrees, that means that the humidity is very high as well. Cold air cannot hold much water, but hot air can. So when air cools down, it starts to precipitate out and condense out its moisture. Okay? So remember, how do you make air cool down? Well, you depressurize it. That's the bottom line. Air, as it depressurizes, cools. That's why if you've ever sprayed an aerosol can, especially, it really does this. I don't know if you've ever played with like a bottle of bottled air duster, like the stuff you spray on electronics. As you spray it, it will get cold. And sometimes it can get very cold, okay? In fact, you can actually with those dusting, kind of like aerosol bottled air dusting things, compressed air, you can actually hurt yourself with those things, especially if you spray them upside down. You spray the liquid out directly. You can actually hurt yourself, give you a cold burn with that. So anyway, as the elevation goes up to the right here, you'll notice that pressure goes down. That causes depressurization, and things get cold as you go up. So as things go up and they move up in altitude, they get cold. As they move down in altitude, they get hotter. Okay? So as air ascends, it cools. As air descends, it warms up. All right, so there you go. There's 10 degrees. We might start off at 10 degrees Celsius. We move up 1,000 meters. We're 0 degrees Celsius. What do we call that change in temperature over the change in elevation or altitude? I'll put A for altitude. The change in temperature or the change in altitude is equal to the lapse rate. Okay. So air will cool according to the dry adiabatic lapse rate. And when it starts to condense out moisture, the latent heat of condensation will offset the DALR, will offset that lapse rate, and it will lower to the wet adiabatic lapse rate, or the WALR, WALR, which is about 6 degrees Celsius per 1,000 feet. 1,000 meters. Okay, so air, as it ascends, how is it going to cool? It's going to cool according to the DALR, until it starts to condense out moisture and form a cloud, and then it will cool according to the WALR, the wet adiabatic lapse rate. Okay, so that's just a review of how those things work. Okay, and remember, there are conditions of stability, absolute versus absolute stability versus absolute instability, and also conditional instability all play into this. Remember, in conditions of stability, air does not want to rise uncontrollably. That occurs when air is cooling down faster than the environmental lapse rate, versus conditions of absolute instability, where air is cooling down not as quickly as the environmental lapse rate. Therefore, the air stays warmer, and it will have a tendency to rise uncontrollably. So when you get uncontrollable rise, you get unstable air masses. So how do you get air to rise? It's all a question, creating weather, creating precipitation, all this stuff. It's really all comes down to a matter of how you get air to rise. So there are a few different ways to get air to rise. You can get it through convection. So like on nice sunny days, you get the air is being warmed up gently from the sun. The land is warming up, and air starts to convect, and it will rise upward and create little puffy clouds that often give us, those are kind of like fair weather days. We get a little bit of puffy cumulus clouds formed from convection of air. So it will rise, it will cool down, and it will return back to the ground in a convective cycle. Okay, so that's one way that you can raise up the air to cool it. Another way to raise up air to cool it are orographic effects. So again, this is all review, but it's good review. You have to remember to understand weather in a deeper sense. So mountains can cause air to rise. As air rises along the mountain, it will have a tendency to cool and condense, and that's going to generate, of course, a lot of rain. So that's why often one side of a mountain will have kind of be more lush, and the other side will be barren. It's because as that cloud reaches the peak of the mountain, starts to descend, it actually warms up, because ascending air cools, descending air warms up. And at this point, it's pretty dry because it's dumped out all of its moisture here on the other side of the mountain. And you get what are called rain shadow deserts on the other side of the mountain here. Okay, so those are two different kind of, I can maybe say, not so catastrophic ways of getting air to rise. There is another way to make air rise, which is more, I can say, kind of creates more violent weather. So that occurs as a cold front moves in. So when you have cold air meeting relatively warmer air, the cold air is more dense, right? So this is dense cold air. It hugs the ground, and it pushes the less dense warm air up, and it will start to condense and form clouds and rain and weather. Okay, that is called frontal wedging. It's a very common process. It happens here in Corpus Christi, and actually it is a very common process all over the eastern half of our country. So if you grew up back east, you grew up in wherever it is, the Midwest or New England area, or maybe you've been here in South Texas your whole life, doesn't matter. But if you're on the eastern half of this country, it's pretty common to have cold air fronts rip roaring in and causing these violent thunderstorms. Okay, so yeah, that's what you need. You need some way of getting air to rise, and that's when it will cool, condense, and form your weather. Okay, so there's all the different ways of getting air to rise up, right? Convection, orographic effects, frontal wedging, and convergence of different air masses. Okay, so as the air masses come together, they converge. They have nowhere else to go but up, and so that's how you get rain in those sorts of situations. Okay, so moving right along. It's supposed to be moving right along. Let's talk a little bit about air masses. So air masses are just big blobs of air that have a certain level of humidity and temperature. So this is pretty easy to understand, I think. But there are two. I guess there are four general types of air masses. Okay. And you can actually kind of make a box like this, and I might actually even have this on your lecture assignment. But you can kind of make a box. It's an ugly box. Let me try to draw one over here that's a little bit prettier. You could almost make a box like this, and you can have warm, cold up here, and dry and wet here. Okay. Now warm, dry air is called, in this box, we're going to call that, get a red pen for this one. This is called CT air mass, the continental tropical air mass. Okay, it is predominant over Mexico. Okay, so Mexico, you know, the north of Mexico is covered with a lot of deserts. It's hot, it's dry, generates a lot of this hot, dry air, and that is the CT, continental tropical air mass. Okay, now a hot, wet one is called the maritime tropical. Now, maritime tropical is a big deal here in the Gulf of Mexico and all over the eastern half of the country. The Gulf of Mexico is a huge producer of maritime tropical air. And this is actually what brings all of the moisture to the eastern half of our country. Take a look at this dividing line of our country. You have the right half, the eastern half, is nice and green and lush. The western half is dry, you know, until you get to California. It's dry. Why is it dry? It's because this maritime tropical air moves in from the Gulf of Mexico, and it really brings a lot of moisture into the eastern half of the country. And that's just how the winds, the normal prevailing wind currents, happen to move air coming up from the Gulf of Mexico. You know, just happens to carry it up and over into the eastern half of the country. That's why, you know, man, during the summers, if you go back east, you're in the South and Tennessee, Arkansas, Michigan, wherever, man, during the summer, it's almost like a tropical rainforest. I mean, it is so wet and humid and hot, and, you know, that's what it's like. So, you know, if you're from California or you're from maybe this side of the country, though, pretty dry. Okay. Oh, I'm sorry, I'm not even done here. I'm just leaving and drinking my tea, and I didn't even notice I'm not finished here. So cold and dry comes from the interior of Canada. That's called continental polar, CP. And the wet and cold comes from kind of the North Atlantic. We call that MP, maritime polar. Okay. So where we are, we get a lot of influence from continental tropical, maritime tropical, but once in a while, kind of especially, you know, during the winter, we can get some continental polar bringing cold air into this area. It happens once in a while. Happened during the deep freeze, you might remember, and those kinds of air masses do make it down even this far south. But, you know, in the rest of the eastern half of the country over here, boy, it is all the time constantly a battle between maritime tropical, continental polar. Maritime tropical, continental polar. It's just like never-ending war waged between those two air masses. And so things will get hot and cold, hot and cold, hot and cold. It usually gets hot, and then a cold front comes in, and et cetera, et cetera, et cetera. So we don't have as much of that dynamic down here in South Texas, but we do get it a little bit. So, anyway, air masses are classified on the basis of those two criteria. The latitude, whoops, I gotta make this red so you can see it. The latitude and it came from, and whether it came from a continental or an ocean. Okay, so it's either going to be, you're really expressing how hot it is, what the temperature of the air mass is, and whether it is how humid it is as well. So moving right along, we have CP and MT air masses are the most important air masses in America. Okay, now in South Texas, it's a little bit different, but really we get a lot of MT. In fact, probably, I mean, where we are, we're almost dominated by MT, with maybe once in a while you get little bits of CT and CP influencing weather, but we are really dominated most of the time by that maritime tropical air. That's why, you know, around here it's always a little bit humid and it's always warm, almost always warm. I mean, of course, there are times that it's not, but really we have pretty stable, warm, moist air here. So continental polar, though, is very important for most of the country. So from northern Canada or the interior Alaska, we get this during the winter, bringing cold, dry air in. However, during the summer, it brings cool relief, but it also brings thunderstorms. So it's very common, you know, when I was in Michigan and Arkansas, it was so common to have in the summer, ooh, it's hot and muggy and sticky, and then a cold front comes rip-roaring in. You get these violent thunderstorms, and then it's kind of nice and cool and dry, and you get a little bit of relief from the hot weather. Again, we don't have as much of that dynamic here in South Texas, but it is a thing in the rest of the country, or eastern half of the country. So anyway, continental polar is responsible for lake effect snows. These are kind of, I just kind of want to show you, I know that we're far away from the Great Lakes, but I kind of want to show you this stuff because it's pretty crazy. Around here where you have the Great Lakes, the continental polar air masses come roaring in from Canada, and they pick up all the moisture from the lakes, and it causes snow on the leeward shores of the lakes. So right here, the leeward, so the windward is this side, the leeward is this side, and so everything you see in blue is their lake effect snows. So you get a lot of lake effect snows in Canada, in Michigan, Wisconsin, especially New York, around Buffalo, New York. Oh my gosh, here's a picture of lake effect. Buffalo is one of the worst. Get lake effect snow in Buffalo. This is when I was out in University of Michigan doing my PhD. There was a day we got pretty heavily hit. Now, in University of Michigan's pretty close here to Detroit. It's in Ann Arbor, a little bit to the west of Detroit. But we got like a 14-inch snow. On that same day, Buffalo got 8 feet. 8 feet of snow. It's disgusting. I mean, you know, and this is what it looks like, right? That's what it, you know, something like 8 feet of snow can look like. You're just totally buried, you know. So anyway, that's, you know, it's a relatively, I won't say it's a common occurrence, but it happens. You know, it happens every few years. So anyway, that's what CP is like. MT, again, this is hot, moist air from the Gulf of Mexico. It's bringing in very unstable, moist air and brings a lot of the precipitation, a lot of the wetness that we get in the eastern half of our country is brought by the Gulf of Mexico through MT air masses. Now, maritime polar doesn't really play a big deal in the United States except for New England. So in New England area, you get the occasional what's called the nor'easter. You know, if you have the New England accent, when you call it northeaster, you'd call it a nor'easter. But the nor'easters come from the North Atlantic, cold, polar North Atlantic, very moist and very cold air, and it brings with it a lot of precipitation, low temperature snows. Here's a nice little picture of Alexandria, Virginia, after a nor'easter. So those are pretty common occurrences in New England area, and you know, of course, as far south you can see as Virginia. So weather is generally produced by two things. It's when air masses, it's basically from movement of air masses, when different air masses meet together. So the leading edges of those moving air masses are called fronts. So sometimes, you know, prevailing winds will change, the jet stream will change, whatever the big air currents. You might remember that, right? I showed you this before. Whoops. You know, here are the prevailing winds shown in real time over the surface of the Earth, right? And you can see that, of course, wind currents change, and you can get new fronts brought in, new air masses brought in from different places. And of course, you can see here comes those right here in Corpus Christi. You can see how the air from the Gulf of Mexico is blowing right on us, right from the east. So we're getting. That's actually why right now, if I look outside, it's kind of humid out and rainy, and that's what's going on. So the air currents move the air masses around, and that's what creates our weather. So the leading edges of those moving air masses are called fronts, and you either have a cold front with relatively colder air coming in, and cold fronts are always shown with this. I really shouldn't have used red. I really should have used blue, right? So cold fronts are always shown, with blue spikies. Okay, so that's a cold front. Okay, warm fronts, on the other hand, are shown with these red, I don't even know what that's called, scalloping almost. Okay, so that's a warm front. Okay, so local high pressure and low pressure patterns also play a big deal here, play a big role here. So remember that when air is ascending, it's rising, the air is going to cool down and it's going to create a low pressure system. And when it's descending, it's going to warm up and create a high pressure system. Low pressure systems are when you get storms, okay, when like stormy weather, rain, precipitation, hail, thunderstorms, tornadoes, hurricanes. Those are all low pressure systems. High pressure systems is when you get nice fair weather, nice sunny weather. It's good fishing weather, in my opinion. Of course, not all the time. Sometimes it's good to fish in the storms, but generally it's nice sunny day. You want to go outside and spend the day outside. You're probably in a high pressure system. It's usually hot, dry, and sunny. Okay, so a front is a boundary that separates air masses. Okay, it's the leading edge of an air mass of different temperatures. So air masses retain their identities. They don't really mix. So the warmer air is less dense and is held aloft, and cooler air is denser and it acts like a wedge. So when cold air comes rip-roaring in, it's going to lift up that warm air, and it's going to cause air to rise. And if that rise is absolute instability, you're going to get these thunderclouds develop with convective cells. Okay. You get these convective cells of air moving up, moving down, a lot of vertical movement of air. It's going to create very unstable conditions and when you get violent weather. So on the flip side of things, so that's what, cold fronts are violent. Warm fronts are the opposite. They are kind of like, that's when you get kind of like nice, gentle rain all day, a lot of drizzle. Sometimes we have weather like that. So warm fronts happen when hot, humid air replaces cooler air. Now, when the warm air is attacking and it's replacing the cold air, it gets up on top of the cold air, right? So it's not going to displace the cold air and lift it up, okay? So the warm air is going to get up on top of the cold air, and it's going to create this kind of progression of clouds. So usually you'll start off seeing cirrus clouds, followed by cirrostratus, then altostratus, then nimbostratus, and then you start getting nice, kind of gentle drizzle. But remember, we're not going to get very violent weather because as the air tries to ascend, if it tries to ascend, it's going to hit this warmer air, and it's not going to be so. The warm air is it's not dense. So air is going to have a tendency to try to rise, but then it'll sink and kind of fall on this leading edge here. So we're going to have nice, stable air here. This is kind of creates gentle rainstorms. So probably you've experienced things like this where you just have kind of like nice, gentle drizzle. It often lasts a long time. It might last all day. It's kind of when you have those drizzly, rainy days. They're kind of nice to sit at home and read a book kind of weather. I guess nowadays people like to binge watch Netflix, but it doesn't matter. That's a warm air front. So there you go. There's your warm air front there with Cirrus. So, by the way, this is actually kind of cool thing. You can impress your friends. You know, if you see cirrus clouds and they're slowly gaining strength, becoming thicker to cirrostratus, to altostratus, to nimbostratus, you can tell them that, you know, it's a warm air front. You'll make a lot of friends that way. No, you won't, actually. They hate to hear about things like this. I've tried. So, well, it doesn't matter. But anyway, that's a warm front. Here's the kind of weather that comes from warm fronts. So you have stable air masses forming stratus clouds. Now, cold fronts are the opposite, okay? In cold fronts, these are not nice, gentle things. Cold fronts are nasty little buggers. Cold fronts have very steep leading edges. They move very quickly, and they're very dense, cold air, and they lift that, they just push very rudely, push that warm air right out of its way, lift it up, and you start getting, you can imagine the air here that's relatively cold, pushing this warm air, and you get instability, unstable air, a lot of vertical movement of the air. So these are very steep leading edges. They are advancing very quickly, and they are associated with violent weather, intense precipitation. The rain is shorter. It's not like all-day storms. It's one of those quick thunderstorms. Maybe it lasts 30 minutes. Maybe it lasts maybe an hour. Sometimes it lasts 5 minutes, you know, but you get these very quick, violent storms. Vertical movement of air is when you get hail, you get lightning, and you get even worse, tornadoes, everything, right? So get those cumulonimbus clouds, those thunderheads, heavy precipitation along the leading edge. And sometimes you can see these things advancing. I love this picture. It's because it's just a very visual. You can see the cold front coming in here, right? I mean, you can literally see the leading edge of that cold front. You can see how steep it is, and it's advancing, okay? And it's probably going to dump rain, right? You can actually see the rain starting to come down over here, right, in this area. So anyway, you can pick these up with, pick up these kinds of, that precipitation, that heavy rain with Doppler radar, and you can see very, very clearly the leading edge of this storm. So very sharp, very fast moving storms, okay, come from cold fronts. So you get unstable air from cold fronts, where you get convective cells, air moving up, air moving down, very unstable, okay? So thunderstorms always involve vertical movement of air. You need to have unstable air and vertical movement of air to generate thunderstorms, okay? Things like tornadoes are the worst kinds of thunderstorms, okay? So the air pressure at the interior of a tornado is up to 10% lower than the outside. So that's what generates those very intense winds. One thing that's kind of interesting about tornadoes is that we here in America, there are tornadoes in other continents, and actually I think there are tornadoes in just about every continent, but Tornado Alley in the United States, of which I don't know if you'd say we are exactly part of Tornado Alley here in Corpus Christi, but Texas definitely has a lot of tornadoes. In fact, Texas has more tornadoes than any other state, but of course it's also very big, so it's a little bit unfair. But anyway, we get a lot of tornadoes here in Texas, and you can see the way they draw Tornado Alley here, they wouldn't include Corpus Christi, but we do get tornadoes in Corpus, so it does happen, but it's pretty rare. Tornado Alley is really intense. I mean, we have way more tornadoes in America than any other country. I mean, way more. Like the second runner-up maybe is China, and it doesn't see anywhere near as many. I mean, we have like 10 times more than second runner-up. So we get a lot of tornadoes. Why do we get a lot of tornadoes? The reason we get a lot of tornadoes here in America is because we have, this is typical, this is typically what happens. We get CP air coming out of Alaska and Canada, the dry interior, and then we have MT air coming out of the Gulf of Mexico, and it's meeting here over the very flat, broad Great Plains. Now, topography plays a role here. You know, the flatter the area, the more conducive it is to. It's kind of crazy. It's really a perfect storm what we have here in Tornado Alley. It has a lot of special conditions because the topography is low. You get this MT coming out of the Gulf. You get CP coming out of Canada. But this is where the big instability lies. The fact is, right here, you have the Rocky Mountains, right? You have the Rocky Mountains through here. So what happens is that you have cold air coming up off the Rocky Mountains, and it's high. It's high. And that's unstable, right? Because then if you think of a cross section, so thinking about this coming, think about this coming out of the side view now. You have, I wish I kind of just had a blank. I'm just going to kind of draw here. So here are the Rocky Mountains, right? And then you have cold air coming out off of the Rocky Mountains from Canada. And then it's coming up on top of, it's coming up out on top of, your MT air, your hot air, and it's colliding with it, right? But the cold air is on top. So that creates a lot of instability because cold air wants to sink. So that's what generates this. You get these sinking air, right? And it's going to generate, that's what starts to generate these cyclones. So I have a video for you that's going to kind of explain it a little bit more with some pictures. It's a pretty good video. It's only a minute, 50 seconds, so I'll play it for you.
Tornadoes occur on every continent except Antarctica, but more form over the central United States than anywhere else in a zone called Tornado Alley. That's because conditions in the alley are ideal for creating tornadoes. Warm, humid air low to the ground moves north from the Gulf of Mexico and collides with cool, dry air high above the ground rolling in from the Rocky Mountains. The collision of air masses creates a supercell, a massive thunderstorm that has a strong rotating updraft of air. Scientists aren't exactly sure what happens next, but the leading idea goes like this. The difference in speed between the faster high winds and the slower low winds causes the air in between to rotate around a horizontal axis. If one end of the rolling air gets caught in the updraft, it's bent upward and forms a funnel cloud. Its spin gets tighter and faster, and the cloud gets longer. Rain or hail from the thunderstorm can then push down on the tail of the funnel cloud till it reaches the ground, forming a tornado. The top wind speed of most tornadoes is usually under 110 miles an hour, and most are on the ground for less than 10 minutes. However, extreme tornadoes are truly extreme. The longest tornado path was cut by the Tri-State tornado on March 18, 1925. It tore up property for 219 miles, was on the ground for well over 3 hours, and killed 747 people. Which is why I'll be hanging out here in Antarctica with the penguins until tornado season is over. For Scientific American's Instant Egghead, I'm Mark Fischetti.
Okay, so there you have it. I thought he does a pretty good job of explaining how tornadoes form. So, anyway, there's tornadoes. Here are different tornado tracks shown. The yellow ones that you see are F5s. So those are kind of very devastating ones. Kind of orange paths are like F2, so they're relatively severe, and the red ones that you see are pretty small. So you can see around Corpus, we're not getting any of the F5 extreme tornadoes, but we do get little bits, little bits of maybe the less dangerous kinds. So F1s and F2s, kind of things like that. So they do happen around here, but they're pretty rare. So anyway, tornadoes form where CP air masses meet MT. We already covered that. So, and I think we already kind of talked about how this stuff forms. So I'm gonna skip some of this stuff. Tornadoes are detected using Doppler radar. So Doppler radar works by sending out a radar signal. It bounces off of, in this case, it's the example is an aircraft, but it can also bounce off precipitation. So the radar is able to bounce off the precipitation, And if the precipitation is moving very fast, take a look at what's bouncing back off of the airplane that's moving. You notice how those waves are closer and tighter together. Okay, so depending on how tight together the reflective radar waves are, we can figure out how fast that rain precipitation is moving. And if it's moving, 100 miles an hour, that is a signal that, we have some extreme tornado weather in sight. Tornadoes also kind of one way. This is also a pretty cool video. I don't want to show the whole thing because it's 6 minutes, but this is a really good. I like this one. One thing, like one warning sign that there's a tornado forming, is you start to see these green skies. So if you ever see green skies, it's a indication you want to get out of that situation, right? So I like this video though because it's got a lot of good pictures of tornadoes, good footage of tornadoes.
The entire planet's tornadoes are reported in the United States. Here, unique geography is ultimately responsible for the high frequency of extremely powerful storm cells. Though tornadoes most often make the headlines, all this excessive energy in the atmosphere can result in a freak show of other wonders. Many of the phenomena we are familiar with, and others we are still just discovering. Not only is Mother Nature's fury amplified with these explosive storms, so is her beauty.
I kind of want to show you something of the green skies. They're kind of cool.
Storm updrafts most frequently erupt near late afternoon.
I think it's here. Oh yeah, there we go. That's really crazy looking.
The order of its colors are reversed.
It's a double rainbow. Yeah, look at that crazy turquoise sky. That's tornado.
Concentrated downdraft of heaviest rain and hail is the core. This icy waterfall often has a turquoise hue. In the evening or morning, when golden hour sunlight mixes in, the storm can turn an eerie green.
So water, that excessive amount of water, of icy water falling, refracts light and scatters light waves, just like deep pools of clear water will appear turquoise. Like if you go to places that have maybe a lake or maybe tropical waters that are very clear, have to be very, very clear, it will diffract light and scatter light waves so that they appear like a beautiful turquoise blue. So that's really what you're seeing here. That's why you get this eerie sort of turquoise color in the skies. And he's saying, sometimes when that mixes with the golden light, kind of near sundown, you can be kind of more of a greenish color. But anyway, that's what's going on that creates that eerie green light that usually precedes a tornado.
In a wind-sheared environment, cell updrafts may rotate, becoming a mesocyclone. This mesocyclone is the defining character of the rarest and most violent breed of thunderstorms, the supercell. And it's these supercells that are responsible for the majority of the world's violent tornadoes.
So anyway, I just want to show you some little bit of tornado footage because it's just amazing. I wanted to see. They had some really cool one. Oh yeah, this one I thought was really cool. I'll show you this one and then we'll end it. Or we'll end tornadoes. We got to talk about hurricanes and then we'll be done. So anyway, I'll stop there with tornadoes, but let me get rid of that. So yeah, moving on to hurricanes. Of course, here in Corpus, we obviously get hit with hurricanes pretty frequently. probably once, every year we get a little bit of hurricane. That last one we had took out what was that, Bob Newhall Pier, right, on the island. So anyway, hurricanes are intense centers of low pressure, extreme low pressure, so cyclones that form over the tropical oceans, characterized by intense thunderstorm activity. They're really just like super thunderstorm. So here are some of the P3 Orions that the NOAA, the Ocean and Atmosphere, National Ocean and Atmosphere Association, they send out to track these thunderstorms. They're pretty cool because these things fly right into the middle of the storm. You can see them flying above the storm. That's the eye of the storm right there. So they're pretty neat. So here are typical tracks of hurricanes. North Atlantic hurricanes. So the hurricanes that hit us are called North Atlantic hurricanes. Over other parts of the world, they call them different things. Some places they're called typhoons. But they're all kind of the same phenomenon, but we do give them different names. So you notice that a lot of them originate right here between 10 and 20 degrees north. So 10 to 20 degrees north is where they originate in the waters off of Africa. So you'll notice that from Africa, they get blown kind of to the west. The reason that they get blown to the west, again, go back and look at the prevailing winds. So if you look at these coastal waters off of Africa in the North Atlantic between 10 and 20 degrees north, you'll notice that a lot of these winds, they're blowing what direction? They're blowing to the west, right? They're all blowing to the west. So that's what carries hurricanes kind of on a path, blows them over towards our direction on a collision course with, either with Texas or Mexico or the Caribbean or Florida, North Carolina, whatever it is, okay? So anyway, that's why we get a lot of hurricanes. They often get blown to a collision course with us. Here in purple, you can see the Hurricane Katrina path that was so devastating, 2005. So we categorize these from Category 1 to Category 5. Category 5 has winds over 155 miles per hour. So what do you need to make a hurricane? Well, the first thing you need is some hot water. So that's why hurricane season is usually peak around August, September. It's because hurricanes need that hot water. So the hot waters here off of, close to the equator, they've been warmed up all summer long. Now they're around 80 degrees, 26 degrees Celsius. So we need that hot water to generate the moisture that's going to power the hurricane, okay? We also need some of these trade winds, of course, to blow them over into our direction. But we also need, especially, a little bit of latitude. So we cannot have hurricanes form right on the equator. They need to form at between 10 and 20 degrees north. The reason that they have to form around there is because, remember, at the equator, we have no Coriolis effect. Over the, you need to get a little bit off of the equator, so 10 or 20 degrees north, just to get a little bit of Coriolis effect to start the spin, to start the spiral, okay? So again, like I said, hurricane season is peak around August and September. Okay, so between August 4th and September 23rd is the worst time. But you can get hurricanes all the way up through October. You can even get hurricanes as late as December, but it's rare. And usually any hurricanes before August 4th are pretty rare as well. So peak, like I said, is between August and September. Now, what do you need to get a hurricane? So you need the hot water. You need a little bit of latitude. You need a trough. You need a low pressure disturbance, because remember that hurricanes form from extreme low pressure cells, okay? So you need some kind of low pressure disturbance that originates off of the coast of the Sahara, usually the Sahara Desert, okay? So you got the high water temperatures. You have the high atmospheric instability, high humidity, and you have far enough north to get some Coriolis effect. You have the low pressure disturbance. And another thing that is a little bit weird, I know, but you have to understand, is that you also need low upper level wind shear. So you need to have pretty low winds kind kind of like a low jet stream. Okay, you need high altitude winds to be low. If high altitude winds are too high, it will blow apart the storm. Okay, so that's why it's another reason, you know, these things have to be kept far away from the jet stream. If you have a jet stream that's dipping down too low during this season, it can blow these apart. So there you go. There's Hurricane Katrina, which is a Category 5, really devastated New Orleans. As you know, you can see there's flooding in New Orleans all over the place. I'm going to show you a quick video just on how hurricanes form. It's a very good video, and then we'll wrap up there. So I'm going to get rid of this, and I'm going to show you this. So this guy gives you kind of some history about the name hurricane, but I'm going to kind of skip over that stuff.
Probably the most famous. These storms are some of the nastiest monsters that Earth's game makers throw our way. A fully formed hurricane can reach more than 100 miles across. Walls of clouds and ice can extend up.
So what I like about this video is he actually explains hurricanes as like a thermodynamic engine, which is what they are. And that engine runs off of the latent heat of water. So what is actually powering the energy of a hurricane is the latent heat of water. So he's going to explain this here in just a minute.
Through the entire lower layer of our atmosphere. But how does a storm that big even happen? The basic ingredients for a hurricane are pretty simple: heat and wind. The wind is easy. Wherever we find low air pressure, air wants to move from the outside in to fill that low pressure. This is what creates a hurricane's super strong winds. But it doesn't explain why they spin. A hurricane's winds want to move in a straight line, but their path is deflected thanks to the Coriolis effect. If Earth wasn't spinning, hurricanes wouldn't either. A 100-mile-per-hour wind blowing north near the equator is also moving east along with the direction of Earth's rotation. Because Earth is basically a sphere, the closer we get to the poles, the slower the rotation. So as that wind moves north, the atmosphere and the Earth below it aren't spinning as fast, and the sideways motion of the wind outruns Earth's rotation, pushing it east. The same thing happens for the winds on the other side.
So it always deflects. In the northern hemisphere, we always deflect to the right.
This is why cyclones spin clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, or anti-clockwise, or whatever. It's also why hurricanes can't form too close to the equator. There isn't enough difference in rotation at low latitudes to start them spinning. Moving in closer to the eye, hurricane winds increase in speed because of angular momentum, just like how a figure skater spins faster when they pull their arms in. The second key ingredient is heat from warm water. A hurricane works a lot like an engine. Not the engine in your car, but an ideal engine, like the one developed by French physicist Nicolas Carnot. First, a piston rises. Now normally, reducing the pressure cools a gas, but in a Carnot engine, heat is added, so the temperature remains constant even as the pressure drops. But what happens if we turn off the heat and keep dropping the pressure? The gas cools. Next, let's reverse the first step, lowering the piston. Now, we'd expect this higher pressure to heat up the gas, but in our engine, we've got a device to draw heat out so the temperature remains the same. And finally, we keep compressing the piston, but we stop taking away heat, so the temperature rises along with pressure. Now, ideal engines like this don't exist in the real world, but a hurricane is one of the closest things we've got. As winds flow towards the center of a hurricane, we'd expect the low pressure to cool them. But the air is kept warm thanks to massive amounts of water evaporating, and I mean massive.
So remember that massive amount of water evaporating is going to lower the temperatures. So you would expect the temperatures to cool, but so this is what he's talking about, where energy is being drawn out by the evaporation of water, and then it's going to be added back in by condensation. That's adding energy from latent heat. So that's why it's like a perfect Carnot ideal engine.
An average hurricane can carry more than 100 billion pounds of water. So how does evaporation keep wind warm? Changing water from liquid to vapor to rip those molecules apart and let them fly free takes energy. This is why you feel cool when you get out of the pool. It's what happens to a bowl of soup that's left out too long. Evaporating water takes heat with it. That heat is stored in the wind, so the temperature stays the same even as the pressure goes down. It's just like that first step of our ideal engine. Then, as the air rises, our heat source is gone, so water vapor condenses into liquid again, releasing its stored heat into the atmosphere. The temperature's actually higher on top of a hurricane, thanks just to the heat released by condensing water vapor. High up, the air releases radiation into space as it flows out and down, just like step 3. And finally, that air sinks back to Earth, compressing and getting warmer, and the hurricane engine is ready for another cycle. This feedback loop turns hurricanes into self-sufficient engines of destruction.
So as long as that hurricane is able to flow over the hot water, which gives it, you know, like I said, it's being powered by the latent heat of the water. As long as it's able to flow over the water, it can gain momentum and gain speed and gain power. And then when it makes landfall, it will quickly dissipate. So that's kind of enough of that video. I'm kind of trying to hurry up and end this. But one of the most devastating things, the last thing I want to touch on is because these hurricanes generate such low pressure systems, they're able to, believe it or not, the low pressure actually causes the water level to rise, and the high winds furthermore blow these large waves. So the combination of the low pressure and the high winds can create these huge waves and huge temporary rise of sea level up to 30 feet. Okay, so that is called a storm surge. Probably you've heard that term before. I'm trying to look if I mentioned this at all about storm surges. But storm surges can really be devastating. I just want to show you one last little video on storm surges, and then we're going to be done. But
aren't the only deadly force during a hurricane. The greatest threat to life actually comes from the water in the form of storm surge. Storm surge is water from the ocean that is pushed toward the shore by the force of the winds swirling around the hurricane. This advancing surge combines with the normal tides and can increase the water level by 30 feet or more.
and probably something like this that took out Bob Newhall Pier last summer.
It can severely erode beaches and coastal highways. The pounding waves can take out boats and buildings. As the waters move in, rivers and lakes may be affected and add to the rising flood levels. While we can't prevent storm surge, we do have a system that can warn us of the incoming threat. As a hurricane develops.
So anyway, I just wanted to show you a little bit of footage from storm surges. So anyway, I'm gonna end it up there. But part of the problem with New Orleans is actually below sea level, so it's a little bit of a problem. But that's why it's so conducive to flooding. But anyway, that's a whole subsidence issue. It wasn't always like that. It's a subsidence issue. So anyway, I'm gonna end it there, and we're all done with weather. We'll move on to the night sky and astronomy next time, and we'll finish up there. That'll be the end of the class. So hope you enjoyed everything, and please email me if you have any problems, questions, or concerns, and start studying for that final exam.